Segment 10, Newton's Laws of Motion. Sir Isaac Newton lived from 1642 to 1727. His mathematical genius was incomparable. He was one of the inventors of calculus, and his work on physics of many different kinds plays an enormous role in the development of modern physics. He was an important figure throughout his lifetime, very famous even in his own time. In order to understand Newton and Newton's laws, we have to do a little bit of a review of some things that you may already know. One of them is the nature of vector quantities. Vector quantities are quantities that have two properties, both magnitude and direction. In our case, we're working in a three-dimensional space. They have a direction in 3 dimensions. Scalar quantities are quantities that have magnitude only. So a common physical scalar quantity that's always scalar is the mass of an object. An object's mass, it doesn't have any kind of directionality about it. But let's consider some common scalar quantities and their corresponding vector quantities. One scalar quantity would be distance, how far something is. But position is the corresponding vector quantity, which we write r with a little arrow above it to designate the vector nature of it. How far something is in what direction, in our case in 3 dimensions. Speed is a scalar quantity for motion. Velocity is the corresponding vector quantity. The velocity is how fast in what direction. Acceleration is also a vector quantity. It's how fast a change of velocity in what direction. So let's ask, why don't we have a parameter for slower? Well, let's look at that. Let's imagine a New York taxi cab. It's moving along in one direction, and you step on the gas. That's an acceleration. The velocity will change. The cab will move faster. The light in front turns red. The cabbie steps on the brakes. The cab will start to move slower. The velocity is changing, and it's changing in the opposite direction from the direction of motion. That's still a change in velocity. That's still an acceleration. So you don't need a slower, because slower is just the same as faster, but in the opposite direction. Let's look at this problem. Here the taxi is getting to the corner of 96th Street and 5th Avenue, and it takes a sharp right turn onto 5th Avenue. Before it was moving at 20 meters a second east, and now it's moving at 20 meters a second south. Has this car undergone any acceleration? Well, the answer is clearly yes. The taxi is still moving at the same speed, but it's moving in a completely different direction. Its direction to the east has gone from 20 meters a second to 0, and its direction to the south has gone from 0 meters a second to 20 meters a second. This last question emphasizes the difference between speed and velocity. Your velocity can be changing while your speed remains the same. This is particularly important in the case of circular motion. An object in circular motion can be moving at a constant speed, but its velocity is changing also, so it needs to be accelerating all the time. The acceleration is constant and inwards. So the acceleration that's needed to make something move in a circle at a constant speed, a, is just equal to v squared over r, where v is the velocity along the orbit and r is the distance to the center of the orbit. The direction of the acceleration must be towards the center of the circle, because that direction is perpendicular to the direction of motion. That's the only way to change direction while keeping the speed constant. If the acceleration vector pointed forward or backward, the object would speed up or slow down. Its speed would change. But if the acceleration is always directly perpendicular to the current direction of motion, the speed does not change, but the direction changes. Notice that this is the acceleration needed to make something go in a circle, and we have not yet said what causes this acceleration. We've just said how big it has to be in order to make the circular motion happen. We can come up with a derivation of this law, a equals v squared over r. And it's a fairly simple derivation. I'll go through it now, and we'll look at it again in class, just to get an idea of where this came from, so you know I didn't just make this up. Let's imagine an object moving in a circle, and it's moving to the right with speed v at the top of the circle, and to the left with speed v at the bottom of the circle. Acceleration is defined as the change in velocity per interval of time. So delta v, the change in velocity, over some time interval, delta t. The velocity in this example has changed by twice v because it was going to the right in the first part and to the left at the bottom. So delta v is 2v. At the same time, the object has gone halfway around the circle. The period of an object is defined as the time it takes to go all the way around the circle. So the time interval involved is 1/2 p. So the acceleration is 4v over p. So what's p? P is the period. That's the circumference of the circle divided by the velocity that something moves along it. The time that it takes to move some distance is just that distance divided by the speed at which you're covering it. So p is 2 pi r, the circumference of the circle, divided by v. So if we substitute this value for p into the equation, what we have is an acceleration that's 4v times v over 2 pi r, or 2 over pi times v squared over r. You'll remember the real answer is a equals v squared over r. The number we've got instead is 2 over pi times the right answer. So pi is about 3, so it's about 2/3 of the right answer. The reason for the difference is that it's not simply stopping going to the right and starting going to the left. It also has to switch from going to the right to going down, and then from going down to going to the left. And that requires somewhat more acceleration. So the coefficient in the real equation is 1, whereas in our simple derivation it's about 2/3. Well, as I said, we'll go over this again in class. Let's talk now about Newton's first law. Newton's first law states that a body at rest or in motion at a constant velocity, that is, moving in a straight line, remains at rest or in motion unless acted upon by a net outside force. What this law is really saying is that the sum of the products of the mass and the velocity of all the objects in a system stays a constant. This is called momentum conservation. M times v added together for all objects has to remain constant in a closed system. So let's give an example of this. Let's take two spaceships, one moving from the left to right and one moving from down to up, that are on a collision course. Each has a mass of 1,000 kilograms, and each is moving at 100 meters a second. So what happens if they collide and stick together? Well, the combined object has a mass of 2,000 kilograms, and it turns out it will have a velocity of about 70 meters per second to the up and right. And that's because it has a mass times velocity to the right from the original problem of 1,000 times 100, and a mass times velocity to the up of 1,000 times 100. But now it has a mass of 2,000, and so in each of those directions it can only have a velocity of 50. And when you add the two vectors with 50 and 50, you wind up with a motion along the diagonal of 70. Newton's second law: a body accelerates in direct proportion to the force applied and in inverse proportion to its mass. F equals ma. This means when you apply a force, when you push on something, if it has a mass of 500 kilograms, it will accelerate twice as quickly as something with a mass of 1,000 kilograms. This is why you need a bigger engine, for example, to get a more massive car up to from 0 to 60 in a given amount of time. You need a harder push if the object is more massive to change its motion than you need if the object is less massive. Newton's third law says that for every applied force, a force of equal size but opposite direction arises. This is the principle upon which rockets are based. It's critical to note that you don't need to push against something with a rocket. As long as you send something backwards, the rocket will move forward. But an equal force does tell you what constitutes a good rocket fuel. If you have a limited amount of space to carry fuel, you want a rocket fuel that accelerates very quickly so that you can apply maximal force to each particle so that each little unit of mass is having as much force as possible imparted to it. That allows you to move the bulk of your rocket in the opposite direction as effectively as possible with a small use of mass.